Hello folks, we are going to review real quick what we had learned last time. That is Coulomb's law. And Coulomb's law starts off with a very important relationship that force is proportional to 1 over r squared. Force is proportional to 1 over r squared, or you can say they are inversely proportional, but it is important to remember that the r is squared. So as one goes up, the other one goes down. If we double the distance, we will quarter the force. So a small change here means a big change right over here. We did not get a chance to talk about this last time, the force versus distance activity. So let's do that right now. Force versus distance activity consists of us listing out a number of different values for r, and then r squared, 1 over r squared, and then for the force. So that means, let's just use real easy numbers. 1, 2, 3, 4, and then 5. 1 squared is going to be 1. 1 over 1 squared is 1. The force that we're going to pair up with that is going to be 100, and we'll explain that in just a few. 2 squared is going to be 4. 1 over 2 squared, or 1 over 4. 1/4 of 100 is going to be 25. 3 squared is going to be 9. 1/9 of 100 is 11.1. 4 squared is 16. What is 1/16 of 100? You all can pop that into your calculators, but it is 6.25. And then finally, 5 squared is 25, and then we can have 1/25 of 100. We're going to end up with 4. Now you say, well, great. What does that mean? What are we getting at here? What I'm trying to show is that a small change in the values over here means a huge, huge, huge change in the values over here. And to help get that across, let me tell you about this new grading system I have. The new grading system goes along like this. If you don't miss any of the problems, of course, that means you got -0, so of course you get 100%. If you miss one of the problems, if you just miss one of the problems, you still get a 100%. You say, oh, wow, there, we love you. You're such a great teacher. I say, I know. And then, let me tell you what else. If you miss 2 of the problems, guess what you end up with? You end up with a 25%. I don't know about that. If you miss 3 of the problems, you end up with an 11%. Well, 11.1%. Let's be fair about that. If you miss 4 of the problems, you end up with a 6.25. 5 of the problems, you end up with a 4%, and so on and so on. If I were to ask you, does that sound reasonable, acceptable, you'd probably say, no, that's outrageous, and we're going to protest. And I would say, well, why is that? Then you'd say something like, oh, well, it's just a small little change from here to here. It's a huge change from here to here. And I'd say, wonderful. That means we don't even have to install this new grading system, because you all have understood the point. A small little change right here, simply doubling that distance, will quarter the force. Hopefully that makes sense to us. Okay, now we move on. We are going on with force and charge size, and this is stuff that we had talked about before. Force is proportional to the product of the charges. It's not just one charge, but it's really the product of the 2 charges. Anyhow, if we put all that together, we end up with Coulomb's law, which is force equals K, Q1, Q2 divided by R squared. Now this value for K is right down here, easy enough, 9 times 10 to the 9. You can program that into your calculators the exact same way we programmed in the value of big G when we were doing universal gravitation, although you don't really need to. It's completely up to you. I figure 9 times 10 to the 9 is pretty easy. But speaking of universal gravitation, oh, there, what do I notice about this? I notice that this equation is almost the exact same thing as the universal gravitation equation. Well, thank you very much for noticing that. It is force is equal to some constant times the product of the 2 important concepts involved. In this case, it's charges. In the case of gravity, it was masses. And then we divide by the square of the distance in between them. So Yay. Yay. All right. Now, some of us have already worked through this on our own. Coulomb's law, equation number 1. But not everyone has. So let's see if we can understand it here. And let's scroll it down a little bit. Okay, so we have these two charges, and it is very important when we are dealing with these charges to really understand not only the numbers, but also understand what types of charges they are. So for example, let's see. Okay, there's a positive charge here and another positive charge here. It doesn't really say where they are in location to each other than there's a certain distance away, but I'm going to put them kind of next to each other like this. And it says it is 0.030 meters away, and I will call this Q1, and this is Q2. I could call them QA and QB or whatever, doesn't really matter. We are going to use our standard Coulomb's law equation. Electric force is equal to K Q1 Q2 divided by R squared. Well, let's see. Here is Q1. Here is Q2. I can plug them in. And here is my distance right here, and I already know what K is. K is 9 times 10 to the 9, and I plug those in, and I get the fantastic answer of positive 180 newtons. Now you might be saying, there, what does that positive mean? What's going on? Well, that positive means pretty much nothing. All the positive here is telling us is that these are repelling each other, as in they are both positive charges, or they could have both been negative charges. The point is, it's the same sign right here as it was right here. That means they are repelling. So all it tells us is the charges are pushing away from each other. Doesn't necessarily tell us in what direction. If we had a negative sign in here, which, oh look, part B says, what if charge B were negative? Well, it'd be the exact same answer. We'd have the exact same numbers multiplied together, Q1, Q2, except Q2 would be negative, but we'd just end up with negative 180 newtons. And you say, wow, that must mean something very, very important, having a negative 180 newtons, right? You say, no, not really. Okay, it just means they are different signs. One is positive charge, one is negative charge. And that just means they are attracting to each other. See, this is a big thing that's pretty different from when we were talking about Newton's law of gravity. With gravity, all the forces were attractive. Gravitational force is attractive. With electrostatic, we can have positive charges, we can have negative charges, so that we can have them attracting, we can also have them repelling. And that's really the only difference between them. So, as soon as we figure out, hey, this is a positive, or hey, this is a negative, you say, wonderful, now get rid of it. Because just because there is a positive right over here or a negative right over here doesn't mean a single thing. As soon as you say, oh, it's attracting or oh, it's repelling, good. Get rid of the sign because I don't want it to confuse you, as you'll potentially see in example number 3. Now, first, let's do example number 2. Example number 2 is when we're talking about, we've got these 3 forces, and it's the forces between 2 electrons. You say, oh no, I don't have any information about the charge. Oh, you do. The charge of an electron is 1.6 times 10 to the negative 19 coulombs. You say, wait a minute, there's a negative sign. Yeah, but you're going to see in just a moment, they're going to cancel out anyhow. Just same thing as what we were talking about before. You say, well, what equation should I use? It's the only equation we have so far. Force equals K Q1 Q2 divided by the R squared. Yes. Now, how do we solve it for the r? Because that's kind of like what we're looking for, right? The distance in between. R squared equals k q1 q2 divided by electrostatic force. And then we take the square root of each side. And there we go. Now we can plug in these different charges, and they will cancel each other out in terms of the negative signs. The negatives will cancel each other out. So what we can actually do, if you are being really, really super spiffy about this, you could actually say R is equal to charge of an electron, or the absolute value of the charge of the electron, if you'd like, times the square root of K divided by, and this is in there, the square root, the force, okay? I took out the charge because I knew the charge was going to be squared. You don't really have to if you didn't really follow along with what I was just saying there. Now, you do some quick number crunching, and you end up with RA is equal to 0.01 meters. RB is equal to 0.02 meters. And RC is equal to 0.04 meters. And you say, what's that mean? Well, hopefully it's rather obvious what type of pattern we have here. It is getting larger, and it is doubling, going from 0.01 to 0.02, I'm doubling. 0.02 to 0.04, I'm doubling. That mystery is solved. But what is happening over here with these forces? If we were to take 5.76 and compare it to 1.44, well, we'd say, well, obviously 5.76 is larger, and then the 23 is even larger than that. Well, yes, but if we take 5.76 and divide it by 1.44, guess what we learned? It's equal to 4. And the same thing is if we take this charge and divide it by this charge, 5.76, we'll also end up with 4. You say, what does that mean? It seems that when I am going in this direction, I'm increasing the size. And when I'm going in this direction, in terms of force, I'm decreasing the size. I'm doubling here, and I'm dividing by 4 this way. I'm quartering it. Oh my! This means I'm ending up with the whole force is proportional to 1 over the r squared relationship. Yay! Yay! How wonderful! Now let's move on. Oops, I need some space. And that's not giving me some space. That was foolish. Okay. Oh, what's going on here? Okay. That was not prepared very well. But oh well. Now I'm dealing with Coulomb's law, example 3, 3 charges. And in this case, you might be saying, holy cow, what do I do? I'm going to have charges A, B, and C. Okay, here is charge A. And A is negative. B, over here, B is also negative. And then there's C. And C is positive. As you can see from the directions, it's over to the left. And there's actual distances that are given in between them. As we're able to notice, this is 0.03 meters to the left. So 0.03 meters. And then we have 0.04 meters this way, 0.04 meters. And then it gives the actual values. This is the negative 6 times 10 to the minus 6 for A. And then we have the negative 3 times 10 to the minus 6. And then we have the positive 1.5 times 10 to the 6, or negative 6. So you say, okay, fair. What do I do with these? Because I'm trying to figure out what the net force is on charge A. To figure out what the net force is, we use our standard Coulomb's law equation. Force equals K Q1, Q2 divided by R squared. Now I'm going to call them QA and QB and stuff like that, just so we can kind of follow along with them. And you say, oh, but what about charge C? Should I just multiply right here? I should say, oh yeah, and then times QC. No, because that's just making up equations. So let's get rid of that. Okay, what we got to do here is we got to say, hey, what's the force of B on A? The force of B on A, well, let's see. I know already that because these are both negative, that it's going to be a repelling force that way. And if I do my quick calculations, quick, I've got my value for K, which is always 9 times 10 to the 9. I have my charges, which I just discussed a moment ago. And then my distance here is this guy here. And I tap that into my calculator, and I end up with positive 101 newtons. And I said, oh, look, I got a positive. Immediately get rid of this positive sign because I don't want it. You say, why? Oh, yeah, because it just means we're repelling. Yes. And in fact, it might confuse us even more because notice what did I draw out earlier? It's a repelling force. It's going to the left, to the left, to the left. Anyhow, 101 newtons. It's 101 newtons that way. Now, switching over to green, force of C on A, I'm going to use K, QA, QC divided by R squared. And just to clarify what that distance is, that's the distance from A to C. Okay? And I'm going to plug that into my equation, so the distance being the 0.03 meters. So I plug that in, and I get 90 newtons. Once again, to the left, to the left. Anyhow, this time it was a negative. You say, oh, but what does that mean about the direction? Well, both of them are in the leftward direction. Okay, so that just means I'm going to add the vectors together. My resultant is going to be something along those lines. Well, let's see, 101 and 90, because remember, I'm just getting rid of this negative sign. 101 and 90 newtons is going to be 191 newtons. To the left, to the left, to the left. Or you could say 191 newtons at 180 degrees. Okay. It is important that we are giving some type of direction here because it is physics, it is vectors, so on and so forth. All right. Now, what we need to do is scooch on down here. We've just gone over all the examples. This would be a good time for you to summarize Coulomb's law. And you can talk about the relationships. You can talk about the whole proportionality thing. Force is proportional to the product of the charges. Inversely proportional to the square of the distance between them. You can talk about that whole positive negative thing, just telling us about whether they're repelling or attracting. You can talk about how to add forces together when you've got multiple charges, as in more than 2 charges, I guess. And if you didn't really understand that, luckily, we have some amazing how-to videos on Blackboard. Watch those. Yeah.